la seva part, la doctora Emma Hayiou-Thomas és professora del Departament de Psicologia de la Universitat d'Oxford i, tot i que per la seva joventut no té el currículum acadèmic com el del doctor Butterworth, el seu background científic és també impressionant i de ben segur que quan la tornem a convidar dintre d'uns anys, els seus treballs encara seran de més referència per nosaltres. La doctora Hayiou-Thomas està en un dels millors centres del món en quant a recerca en neurodesenvolupament i trastorns d'aprenentatge. Entre els seus treballs, m'agradaria destacar la línia enfocada a identificar factors de risc de les dificultats d'aprenentatge i de la lectura en particular, en edat preescolar. La doctora Hayiou-Thomas té diversos treballs en els que estudia la relació entre les habilitats lectores i de llenguatge en edat preescolar i el rendiment en edats posteriors, identificant com a principals factors de risc per la dislèxia i el rendiment baix en tasques d'identificació de lletres, en lectura, de pseudoparaules, en consciència fonològica i en la rapidesa en la denominació. En el seu darrer treball, Developmental Dyslexia, Predicting Individual Risk, publicat al Journal of Child Psychology and Psychiatry, podeu llegir aquests resultats. Avui ens ve a donar una visió integradora de la dislèxia, concretament de les característiques de desenvolupament d'aquest trastorn, de la seva etiologia i de la comorbiditat amb altres trastorns.
Buenas tardes. The rest is in English. But thank you all who've made it this far in the day. You've done really well. Congratulations. We're nearly there. And thank you very much to the organisers for inviting me today. It's a pleasure to be here. I should just clarify I'm currently at the University of York in the north of England. We like to think it's just as good as Oxford. Okay, what I'd like to do today is present a perspective of dyslexia to you, which has emerged from recent work in behavioural genetics. And the ideas that really are key here are that it's best conceptualized as the extreme end of a continuum of reading ability, and that this continuum of reading ability is underpinned by multiple risk and protective factors, both genetic and environmental, and that an accumulation of these risk factors is what ultimately leads to very poor performance, which is what we call dyslexia. So what I'm going to do is give you just a little bit of background about basic characteristics and precursors of dyslexia. And then I'm going to give you some data on the etiology of dyslexia. And then I'm going to move on to talking about the relationship between dyslexia and a couple of other disorders, comorbidities with specific language impairment and also with ADHD. And what I'd like to, my take-home message really is that one very, in my view, compelling way to view developmental disorders like dyslexia is from a multiple risk model perspective, because if you put together the idea of a continuum, a distribution of ability, and you put that together with the idea of multiple risks that each influence different aspects of cognition and development, it's quite a parsimonious way of explaining the very frequent comorbidity we see between complex disorders. So much of my work over the last 10 years has been in two parallel long-running studies, one of which uses quantitative genetic methods and twin analyses as part of the twins early development study. This is based at the Institute of Psychiatry, headed by Robert Plomin. And the sampling frame for TEDS is all the twins who were born in England and Wales in the mid-90s. So we started the study with 15,000 children. And we have longitudinal data on these children from the age of 2. They're now finishing university. I have some students at York who are TEDS twins. And we have measures on their language, cognitive, and behavioural development over this very long time period. So this size of sample is very powerful for doing quantitative genetics. The downside is that the depth of measurement can be limited when you have to deal with this many people. There just isn't the time and the money to do the in-depth measurement that you might like to do with 15,000 people. So the Wellcome-funded Language and Reading Project on the right-hand side there, based at the University of York, has a sample of 260 children, 100 of whom were at high family risk for dyslexia because one of their first-degree relatives, a parent or a sibling, has dyslexia. And we compared these children with children who had an early speech or language difficulty, as well as a control group. And with this slightly smaller, well, rather smaller sample, we've got very in-depth measurement of language and pre-literacy and literacy measures from the age of 3 through to the age of 9. Okay. So dyslexia, according to the most recent edition of the DSM manual, the 5th edition, is a pattern of learning difficulties that's characterized by problems with accurate or fluent word recognition, poor decoding and spelling. And this occurs despite general cognitive ability that's in the normal range and despite adequate instruction. It's classified as a neurodevelopmental specific learning disorder. It persists over the life course, and its prevalence in the general population is estimated between 5 and 10%. And as I said, it's conceptualized as the extreme low end of a distribution of reading ability. There's nothing very special in the way that children read who fall below this rather arbitrary cutoff compared to children who are just above that cutoff. So there are now some well-established precursors of dyslexia. They're very predictive of reading ability, whether good or poor, and these are things that you can measure in preschool. Two of the key ones are phoneme awareness, the ability to manipulate phonemes and phonemic units in spoken words, and the other is knowing your letters, so knowing the names or the sounds of letters. And these two together give rise to the alphabetic principle, the idea that you can map phonemes and graphemes in a written alphabetical language. A third factor that is also highly predictive, particularly in regular orthographies, is rapid automatized naming, in which you have very rapid cross-modal retrieval of the phonological code. And there's been a lot of cross-linguistic work, and a very nice recent study by Karavalos et al. Looked at Spanish, English, Czech, and Slovak using the same battery of tests, and found that these core predictors were indeed predictive to a similar extent across these 4 languages. So phoneme awareness, letter knowledge, and RAN were predictive of reading nearly a year later. So that's the kind of backdrop. What I'd like to tell you now is about the idea of dyslexia as a heritable disorder. So we've known for a really long time, over 100 years, that dyslexia runs in families. And in fact, there's a very nice quote from 1907 saying that congenital word blindness may assume a family type and a hereditary tendency is probable. And we know that the prevalence in family risk samples is nearly 10 times, or between 5 and 10 times the prevalence in the general population. So nearly 50% of children who are growing up in a family with either a parent or a sibling who's dyslexic are also likely to develop dyslexia. So there's a recent review by Snowling and Melby-Lervag looking at family risk studies in a number of different languages which vary in the opaqueness of the orthography, so from very opaque orthographies like English through to very transparent ones like Finnish. And children, the approach in family risk studies is that you can recruit your sample when they're very young because you're doing it on the basis of their relatives, not the children themselves. And you know they're going to have a high risk of developing dyslexia later on, so you can look at the early precursors of dyslexia. And what typically these studies do is wait a few years, measure the kids at multiple time points, see who turns out to be dyslexic, and then go back to your data from earlier time points and see what characterized the children who did and did not develop dyslexia. And so in this meta-analysis by Snowling and Melby-Lervag, they showed that when you look at literacy outcomes at the age of 8 and you compare those children who, although all at family risk, went on to develop dyslexia or did not go on to develop dyslexia, you can see that the dyslexic group are severely impaired on literacy measures. So word reading, non-word reading and spelling, classic word level literacy measures, they're impaired. Unsurprisingly, they're dyslexic. This is by definition. What's interesting is that the children who didn't go on to develop dyslexia have mild but significant impairments in these literacy skills as well. So although they didn't meet diagnostic criteria, there clearly is some residual low-level deficit there. This is quite dramatically apparent in the early years. So again, if you take these same 2 groups and compare them on their early performance, what you can see is that there are deficits not only in the dyslexic group, which we would expect, but also in the children who didn't go on to develop dyslexia. And in fact, their deficits in non-word repetition, which is a very sensitive marker of phonological working memory, are at this equivalent level to those kids who go on to develop dyslexia. So there's very clear phonological deficits that are shared in these families, regardless of who meets diagnostic criteria at the school age. And in fact, at school age, those phonological deficits are still significant in the children who don't have formal diagnosis of dyslexia. So one of the messages that these family risk studies suggest is that, first of all, there's no clear cutoff, that dyslexia is a dimension that ranges from very mild, where you'd call these children unaffected, to very severe, where you have a diagnosed disorder, but that even these unaffected children who are at family risk have subtle impairments in literacy and phonological skills, which you can trace back to the early years and through the school ages as well. And a very useful concept borrowed from behavioral genetics here is that of an endophenotype, the idea that this is an intermediate factor that lies between the genetic risk and the disorder itself. So the idea here is that the phonological deficit is a good candidate endophenotype for dyslexia. So the family risk studies strongly suggest that dyslexia and the phonological deficit that is associated with it is heritable because it runs in the family. But we know that families share their environments as well as their genes, and so a more powerful way of disentangling these factors is looking at twins. Sort of related, I'm actually going to skip this slide, I think, for the benefit of time. The key methodology in behavioral genetics is really that what you're trying to do is map the individual variation that's present in the genome onto individual variation that's present in the phenotype and the behavior that you're interested in. And most of us, if you look at your neighbor, you share almost all your genetic material. So take a good look at them. And you'd think there'd be some substantial differences, and they are there, but they only represent 0.1% of your actual DNA. But because you've got so many base pairs, 3 billion of them, 0.1% of 3 billion is still quite a lot of variability to play with. So there's still 3 million base pairs difference in DNA between you and the person next to you. And what behavioral genetics essentially is doing is trying to map that variability in the genome onto variability in behavior. So the variability that can be mapped onto the genome is what we call heritability, but we also try and decompose behavioral variance into the environmental factors that we know influence behavior. So we can differentiate between shared and non-shared environment. Shared environment is anything that's shared within the family. Non-shared environment is something that's specific to a particular individual in that family. And twins are a powerful method because, unlike most people, identical twins share 100% of the DNA. And fraternal twins share 50% of their varying DNA, like any other sibling pair. So if we see that identical twins are more similar to each other in reading or height or any other behavior that we care to measure than fraternal twins, their extra behavioral similarity is attributed to their extra genetic similarity. And this gives us a handle on quantifying those sources of genetic and environmental variance. You're going to see a few of these balloon models. So I'm just going to explain this one, and then you'll see some kind of expanded versions in a few slides' time. The squares at the bottom are the measured variable, and the circles at the top represent the latent variance that is represented by additive genetic factors. That's the A, the first bubble. C represents the shared environment, and E represents the non-shared environment. And the idea is that these are the latent sources of variance that are driving the measurable, observable variable that you have. And within a twin pair, you've got two twins, twin 1 and twin 2, and the idea is that their genetic sources of variance are 100% correlated, correlation of 1 for identical twin pairs, but only 0.5 for fraternal twin pairs. And the shared environment is correlated to the same degree for both types of twin pairs, and the non-shared environment is uncorrelated by definition. Okay, so using twin models like this, there's been a number of studies across the world, in the US, in Australia, in Scandinavia, in the UK, as well as other countries. These data come from the International Longitudinal Twin Study in those 4 countries at the top, and they all demonstrate very nicely that in 6-year-old children, reading is highly heritable. So as a proportion of variance, the blue bit is the genes, the red bit is the shared environment, and the green bit is the non-shared environment. And you can see there's significant genetic effects on reading, as well as those precursor skills that I showed you earlier, phonological awareness and RAN. Letter knowledge is an exception here, where the environment seems to matter a whole lot more than the genes. Okay, so these findings have been replicated in a number of different samples in a number of different languages. And this slide is essentially to show you that actually, that at the genetic level as well, the amount of genetic versus environmental influence is very similar, whether you're looking across the distribution of reading ability or whether you're focusing at the children at the very low end who meet a dyslexic diagnosis. So we have a very significant blue chunk at the bottom of that bar, which represents the genetic effects on reading, whether it's good or poor. Okay. So just to recap that bit, reading is a highly heritable trait, both in the normal range and the low end of the distribution. The core precursors of reading or dyslexia are also significantly heritable, with the exception of letter knowledge. And although I didn't show you that data, there is in fact significant genetic overlap between the precursors of reading, the phonological traits, and the RAN measures that have been taken, and reading itself. So many of the same shared genetic factors operate on those precursor endophenotypes and on the reading manifest behavior. Okay. So in the DSM, dyslexia and reading impairment is classified under specific learning disorders, which is listed separately from communication disorders, which in turn are both kind of under the umbrella of neurodevelopmental disorders. And this is obviously very useful for classification and diagnostic purposes, but what is very frequently observed is that we have very high rates of comorbidity among many, many of these disorders. And although the rates vary from study to study, there is substantial comorbidity that's been reported between dyslexia and decoding difficulties and specific language impairments. So up to 50% of children who meet criteria for dyslexia also meet clinical criteria for language impairment, oral language impairment. There's comorbidity with speech-sound disorder, with dyscalculia, very well-established comorbidity with ADHD, up to about 40%. Motor coordination deficits, conduct disorder, and emotional difficulties. So it's actually more common to see these overlapping difficulties co-occurring rather than to see a kind of pure isolated disorder. The two I'm going to focus on are the relationship between reading and dyslexia and language impairment, and then with ADHD. So I've talked a little bit about the importance of phonology as a foundational skill for reading, and the fact that both phonological skills and reading appear to be highly heritable and driven by many of the same sets of genes. But of course, language isn't just about sounds. What you say, the meaning of what you say, the grammar of how you construct a sentence, the pragmatics of how you use that in a communicative setting are also very important. And we know that literacy builds on this foundation of oral language skills. But a nice way of conceptualizing the relationship between these different aspects of language was put forward by Dorothy Bishop and Maggie Snowling about 10 years ago. And they proposed this 2D model. And the idea here is that it's a simplified model, and they make that very clear in the paper, but the idea is that it can be useful to conceptualize the phonological dimension as being at least partly independent from the non-phonological aspects of language. So we can think of phonology and broader oral language skills as being two separate, if related, dimensions. And that if you split these out in this way, you can begin to account for some of the patterns that you tend to see. So what they suggested is that children who've got particularly poor phonological deficits, but whose general language abilities are in the normal range, are those who have decoding and word-level reading difficulties, so who would fit the classic dyslexic profile. They suggested that children who have both broad language difficulties and phonological difficulties would be what we call having specific language impairment, and that another group of children who can decode accurately but don't understand very much of what they read, who've been termed poor comprehenders, would come into this quadrant. And the idea here is that phonology is particularly important for driving decoding skills, and that these broader aspects of language are particularly important for comprehension. So one of the things that I was very keen to do with the twin data that I mentioned from the TED study is to test the idea that these two different elements of language, phonology and broader oral language skills, to see whether actually they can be dissociated, whether it makes sense to think of them as independent from a genetic perspective. And so what this model shows you, this is basically an expanded version of that balloon model I showed you earlier. What we have here is a battery of 9 measures that we gave to a subset of TEDS twins when they were 4.5. So we had measures of narrative, retelling, of grammatical skills, of word knowledge and semantics, of verbal fluency, verbal memory, and in fact phonological awareness here. And then these are more output phonology measures of articulation and non-word repetition. And based on factor analysis, it became clear that these 7 measures loaded very well onto a single factor, which I've called language here. So this is a latent factor representing the common variance in all of these. That the articulation and the non-word repetition measures loaded very cleanly onto a factor I've labeled phonology. This is latent factor here. And what we're doing here is decomposing the variance in these latent factors into additive genetic and the environmental components. And what we can also do then is see whether these correlate with each other. So the genetic correlation between language and phonology and the environmental correlation between them. And what this suggests is that both language and phonology, those 2 latent factors, have significant heritable components. In fact, the environment is at least as important for the language component, if not more. Whereas for phonology, genetics, again, as in the previous slide, seem to be the dominant driving force here. And there is a strong correlation between them in terms of the genetic overlap and in terms of the shared environmental overlap. Nonetheless, you can't set this correlation to 1. So these 2 factors have got to stay separate. They're dissociable. Okay. So in that respect, this provides etiological evidence for the 2-dimensional model put forward by Bishop and Snowling, that in fact it does make sense to think of those as partly independent elements of the language system. Okay. Looking at this from the Wellcome Family Risk Study that I told you about, the Language and Reading Project, what we had, just to recap, is children who were at high risk, at high family risk of dyslexia, and comparing these with children who were identified as having language impairments at preschool. And we categorized, so we asked parents about the family risk of dyslexia, either an objective assessment, and we also had a self-report measure. And then we also had objective assessment of language ability at the age of 3.5. And what we have are, these are our family risk sample. This is the language impaired sample. Now, perhaps it'll be unsurprising to you that many of the family risk children also met criteria for language impairment. So of these 112 children, 29 also meet criteria for language impairment. 83 do not. Okay. And what I want to highlight here is that the family risk children who do not have a language impairment are nonetheless quite impaired in terms of their phonological skills at preschool compared to the typically developing controlled children who have no family risk that we know of. Okay, so once again, phonology is popping out as a strong risk factor in this group of children who are at high genetic risk for developing dyslexia later on, and this differentiates them somewhat from this group. If we skip forward now a few years and look at how these kids are looking when they're reading at age 8, this is the probability that these groups would be classified as having dyslexia, or the proportion of children who would meet criteria for dyslexia at the age of 8. So this is what their risk status was at age 3 in terms of family risk or language impairment status. This is whether they still had a language impairment at the age of 8, concurrently with the dyslexia outcome. And what you can see here is that the red and the green bars are the same height. So whether you had isolated family risk or an isolated language impairment, about 25% of those groups went on to meet dyslexic criteria. If you are unlucky enough to have both of those risk factors, both a family risk and a language impairment, your risk significantly increased, and 40% of that group met dyslexic criteria. And a similar pattern is seen here for the risk status at the age of 8, and it's just worth noting that if your language impairment persists into the school years, then your risk for dyslexia is also slightly higher. Okay, so what that suggests is that perhaps, again, this 2D model is useful in giving us some idea of the level of risk and the way in which those risks operate and feed into an outcome of dyslexia. Turning to the twin study now, and I should have pointed out that I've got a little TEDS logo when I'm talking about twin data, and a little Welcome Language and Reading Project logo when I'm talking about welcome data. But I'm addressing similar questions from these two different data sets. Looking at the twin data, what we've got here is, again, the association, the height of the bar reflects the association between having poor language skills at the age of 4 and poor reading skills at the age of 7. So reasonably parallel age gaps to those, to the previous slide I was showing you. And this is the overall association between having poor output phonological skills at the age of 4 and reading at the age of 7. And again, using the twin models, what we can do is break that down into the contributions of genetic and environmental factors. So what's going on here is that we have significant but small genetic influences that link early language deficits and later dyslexic outcome or later reading outcomes, and significant shared environmental influences that really are explaining most of the relationship between early language difficulties and later reading. And you'll notice that the relative proportions of blue and red are rather different here. So actually only the blue bar is significant here. The red bar is smaller and not significantly different from 0. And that means that although there are shared genes between poor phonology and reading outcomes that drive that phenotypic association that we observe, the role of the environment is negligible here. So put together, what those suggest really is that phonological and non-phonological aspects of language, as predicted by Bishop and Snowling's model, do make at least partly independent contributions to reading and to dyslexic outcomes. And looking at it from an etiological perspective, they also have slightly different etiological relationships to reading, whereby phonological deficits are clearly visible in children at high family risk, and there seems to be a genetic pathway that links those early phonological deficits to later reading, whereas the language deficits are less visible in the family risk sample, and there seemed to be an environmental as well as a genetic pathway to reading, linking early language problems and later reading. So that distinction, once again, seems to be quite useful. Okay. So in those previous slides, what I was doing was breaking apart the oral language foundations of reading into phonological versus non-phonological aspects of language. In the next couple of slides, what I want to show you is a breakdown of reading into its important components. So most of the reading measures that I've presented data on here are word-level reading and particularly decoding measures. But ultimately, what you need to learn to read for is to understand the text that's in front of you. So reading comprehension is ultimately the goal of reading. And the simple view of reading put forward by Goff and Tumner in the mid-80s, which is still a very powerful framework today, has a lot of empirical support from a number of different methodologies. And the basic idea is that reading comprehension arises from the combination of decoding skills and oral language comprehension. So you need both of these to be intact and operating well to be a good reader. And if either one of these goes wrong, then that can be a risk factor for reading comprehension. And this is, again, data that is very recently emerging from the Wellcome Language and Reading Project, linking these early language skills to decoding, partly through phonological awareness. But what I want to draw your attention to in this slide is really the direct link, the additional unique variants predicting, contributing to start that sentence again. The additional unique contribution from early language skills directly to reading comprehension several years down the line. So we know that decoding will feed into reading comprehension. That's not surprising, but we also have this additional direct pathway relating these two things. Okay, so flipping back again to the twin modeling, but looking at a similar question again. So breaking down the reading side of the story into decoding and reading comprehension and seeing how those relate to oral language skills. So what we have here is another one of these latent factor models. And again, we didn't constrain the data. We compared this to a fully unconstrained model, and this is the model that came out that came out best. And what became very clear to us is that, in fact, we're dealing once more with two factors that are correlated but cannot be collapsed into one. And what these two factors are one, decoding at the age of 7, 12, and 16, loading onto this latent decoding factor. But the exciting bit for me here is that these are oral language skills here at the age of 7, 12, and 16, and reading comprehension skills at the age of 12 and 16. And these are loading onto a single comprehension factor. These can't be split apart into oral language and reading comprehension. So certainly by the time you're 12, there seems to be no distinction in terms of your linguistic comprehension, whether it's coming through your ears or through your eyes, certainly from a genetic perspective. So these two factors, as I say, are correlated, but again, cannot be turned into one. They have to be kept associated for the model to fit the data. And here we see quite high genetic contributions to both comprehension and to decoding skills. So in terms of the relationship between oral language, decoding, and reading comprehension, what I think this data says is that there are overlapping genetic and shared environmental influences on early language and later reading skills. And importantly, that decoding is etiologically dissociable from reading comprehension. These are two different subcomponents of the reading process that you can see reflected in the underlying etiology, and that there is no such distinction to be made between oral language skills and reading comprehension. These two seem to be indistinguishable etiologically, certainly by the age of 12. Okay. So in this final section, I want to show you some data that's quite recent, looking at the relationship between reading and attentional measures, again from both of these studies. And as I said earlier, we know that there's quite high levels of comorbidity between dyslexia and ADHD in particular. There's a number of reasons why these might occur. So it might be that children who are inattentive can't benefit from reading instruction as well as their peers, or it might be that there's a shared genetic liability that gives rise to both attentional and literacy problems. And so these data are trying to begin to get at how some of those mechanisms might play out. Okay. What we have here is, again, data from the Wellcome Language and Reading Project in preschool children. And what we have on the left are the typically developing group, the family risk group, the high family risk group, and the children diagnosed with language impairments at the age of 3.5. So we also, because we were interested in issues of comorbidity, we had measures of executive function, and particularly attention, as well as fine motor skills. And what you can see, unsurprisingly, is that there's very small proportions of children in the TD group who seem to have difficulties in these areas. There's an elevated proportion who've got difficulties in both of these in the family risk group. But most dramatically, in the LI group, in the language impaired group, there are really quite substantial numbers of children who seem to be having quite serious difficulties, either with their fine motor skills or with their attentional control, or with both. Okay. So what we thought would be interesting to do would be to see whether we know that these three core precursors I showed you earlier from a vast literature, we know they're highly predictive of reading and dyslexia outcomes. We wanted to see whether these executive and attentional skills that we had measured could add to the prediction of dyslexia outcome. And what these data these models are showing are the outcomes of logistic regression models that are trying to make an individual prediction and classification of outcome. So here we have these three key precursors at the age of 4.5 and reading outcome at the age of 8. So we know that family risk is adding unique variance to reading outcomes. But what was novel about this particular analysis was that the executive function tasks are also significantly improving the prediction of the individual children's outcome at the age of 8, so 4 years later, with reasonably good sensitivity and specificity. Okay. This is looking at the same data from a slightly different perspective, and is classifying children in terms of whether they perform well or not on these core precursor skills, so the phonology, the RAN, and the letter knowledge, because those are our bankers. We know those are going to matter. But what we also wanted to do, and the different lines reflect children at high family risk and low family risk of dyslexia. On the left here, you've got the probability of diagnosis of dyslexia at the age of 8. And what we've got up here are the children who have poor core skills and poor executive function. And these children, if they've got this combination of risk factors, seem to be highly likely to be classified as dyslexics several years down the line. More positively, the children who've got really quite poor core skills, so equivalent levels of difficulty with phoneme awareness and executive function and so on, but if they have good executive function skills at the age of 4.5, which in the UK is when they start school and when they start reading instruction, this seems to act as a protective factor, and you have a very steep decrease in the probability of a dyslexic outcome. So this was, in our view, rather a nice good news story, in that although we can think of attention as a risk factor, we can also see that it might have a protective effect if you have good attentional skills that might offset some of those inherited and really usually quite predictive skills deficits that underlie dyslexia. Okay. So children at family risk of dyslexia, and particularly those with language impairments, seem to be more likely to have attentional deficits. And poor attention at the preschool age adds significantly to the prediction of a dyslexic outcome. But good attention can act as a protective factor, even in the context of poor core literacy skills. And this is really the final set of analyses I want to show you, looking at the relationship between reading and ADHD traits as measured in clinical questionnaires. And this is again data drawn from the TEDS twin study. So again, replicating a phenotypic, a behavioral overlap between reading and poor scores on attentional measures, or ADHD measures, ADHD symptomatology. And also, as with previous literature, finding a strong genetic influence on ADHD symptoms and also on reading. And the genetic correlation between these is moderate at 0.31. So it's significant, certainly not the whole story. But we know that ADHD comes in two flavors. It comes as in the form of inattention, or in the form of impulsivity and hyperactivity, and sometimes in the combined form. So what this analysis is really doing is looking at inattention separately from the hyperactivity and impulsivity, and finding that there's a significant association in terms of their relationship to reading. So really, what's carrying the correlation with reading is the inattentive component and not the hyperactive component of ADHD. Breaking this down further, on the reading side now, I've already talked about looking at decoding separately from comprehension, and it looks interestingly as though this dissociated effect within attention compared to hyperactivity is really to do with the decoding aspect of reading. So those more kind of mechanical word level processes that are earlier acquired. So again, here we have a significant genetic correlation between inattention and decoding, but not between decoding and hyperactivity and impulsivity. So in terms of the shared genetic variance, at least, it looks as though it's not really reading in ADHD, but reading in ADD that might be the core of the story. So the relationship between reading and symptoms of ADHD is driven partly by shared etiology, and again I emphasize that's not the full extent of the story, but to the extent that it is, the genetic overlap seems to be between reading and the inattentive components. So finally, what I hope these sets of data that I've shown you today have illustrated is that it makes sense to think of a complex and very common disorder like dyslexia to be conceptualized in terms of these multiple cognitive deficits, which are underpinned by multiple genetic and environmental risk factors. So if you think that we have risk alleles represented in these latent genetic factors here that are particularly important for language, overlapping sets of risk alleles that are particularly important for attentional control, yet again a separate but overlapping set of risk alleles that are important for phonological deficits. If you have a phonological deficit, that increases your chance of a dyslexia phenotype. If you also have a persistent language deficit, that further increases your chances. If yet again you have attentional difficulties on top of that, that increases the likelihood of a dyslexia diagnosis as well. But ultimately, the reason that we see dyslexia overlapping with so many other disorders is potentially because there's overlap at this endophenotypic level and ultimately at this etiological level as well. And that's where I'm going to leave it. So I'd just like to thank all the families who've participated in both the TEDS and the Welcome Language and Reading projects, as well as my collaborators, many more on both projects, but these are the key people I've worked with on these particular data, and of course the funders and your audience. Thank you very much for your attention this late in the day.